Hello and welcome to this lecture on fundamentals of electric drives. In the last lecture, we were discussing about the synchronous motor drives. So, we understood that we have two types of synchronous motor drives. We can categorize them into two types. One is the true synchronous mode, other is the self control mode. So, we have the true synchronous mode drive that we discussed in the last lecture, and in this case the stator frequency is independently controlled. So, it is just like a normal synchronous machine fed from a stator, fed from a supply with a maybe variable voltage, variable frequency. We have other types of synchronous motor drives where we need a closed loop feedback to decide the stator frequency, and that is called a self controlled drive. So, we have the second type of drive which is called the self controlled mode. Here the stator frequency, the frequency of the stator is controlled by the rotor. Now, why it is so? Because in synchronous machine there has to be a synchronism between the stator and the rotor. Now, when we supply it from an independent source, that is the true synchronous mode, that is the first mode. This is a drive which is supplied from an independent source having a frequency f, there is a possibility of instability. The machine may sometimes haunt, sometimes it can oscillate, because the stator frequency is independent of the rotor speed. So, that there will be some situation where the rotor will try to adjust with the stator frequency, that is the instability, which can express in terms of haunting and oscillations. Now, in case of a self controlled drive, what we have, the rotor decides the stator frequency. So, we have a motor in which this is a synchronous motor as before, but in this case we have a position sensor here, or a rotor position sensor, which will decide, this is the rotor speed and position sensor, which will decide the stator frequency. It means there is no question of falling out of step. It basically the motor is controlling itself, and hence it is called a self controlled mode. Now, we discussed in the last lecture about the true synchronous mode drive. So, we have the motors which are connected in parallel. So, we have the synchronous motors here 1, 2, 3. So, we have so many motors connected in parallel. They are fed from a voltage source inverter, and this voltage source inverter is fed from a control rectifier. We have the VDC here, that is the supply voltage, and the VDC, there is a filter here which filters the VDC value, and then this feeds to the voltage source inverter, and the output is AC. So, the output in this case is AC. Now, when we want to change the speed, so what we do here, we change the frequency. So, we change the frequency. So, this is the frequency command, frequency reference. So, the frequency reference, we can apply a step change, but the step change should not be applied to the motor. So, it is delayed by a delay circuit, and then we have the frequency, and we need to keep the flux constant. So, as we have in case of an induction motor, the same thing can be applied to the synchronous motor, that we can keep V by F nearly constant up to the base speed. So, this is the V by F function generator. So, the output of this is the voltage. So, in fact, we have a curve where the y axis is the voltage and x axis is the frequency. So, if we know the frequency, we can find out the voltage. So, this voltage reference is fed to the control rectifier, which decides the decelerating voltage, that is VDC, and the frequency information, the frequency command is fed to the voltage source inverter, which converts DC into AC of the same frequency. This is actually AC of the same frequency, that is F. F is the fundamental frequency, fundamental frequency. So, there is no position feedback here. So, this is synchronous motor drive in true synchronous mode. The disadvantage of this drive, as we have discussed little before, instability. So, the disadvantage of this drive, main disadvantage is hunting and instability. So, this hunting and instability can be taken care by having a drive in self control mode. Let us discuss about a drive, a synchronous motor drive in self control mode. So, we have before that let us see actually the torque speed characteristic. In a true synchronous mode, the torque speed characteristic would be like this. We are varying the frequency here. So, the y axis as before is the speed and x axis is the torque. So, these are the constant speed drive. So, we maintain a constant maximum torque. This is T maximum and this is minus T maximum. So, these are constant speed drives. Synchronous motor drives, if we keep the frequency almost constant, they are almost constant speed drives. So, we get the same maximum torque here. So, this is a frequency, let us say f 1, f 2, f 3, f 4. So, we are basically increasing the frequency. So, f 4 is greater than f 3, is greater than f 2, is greater than f 1. So, we are gradually increasing the frequency. For a given frequency, the speed remains constant. We can vary the speed, vary the torque with the same speed. So, these are constant speed drives. So, let us say this is our rated speed. So, we reach the rated speed here. So, after we reach the rated speed, we do not keep the V by F constant. With the increase of frequency, we decrease, we keep the voltage constant. So, that basically leads to a reduction of the peak torque. So, the drive will follow this nature where the torque reduces. These are, so this is f 5, f 6, f 7, f 8. So, we can say that f 8 is greater than f 7 is greater than f 6 greater than f 5, which is greater than of course f 4. So, this zone is called field weakening zone, field weakening zone from this point onwards. And from the 0 speed, this is actually the origin, this is called constant torque zone. So, we get in this case constant torque. So, as before, the field weakening zone is also known as constant power zone, constant power zone. So, up to the rated speed we keep the torque constant, and after the rated speed we decrease the flux, we do not maintain the torque constant, torque decreases, but the power remains constant. So, this is the speed torque characteristic of open loop synchronous motor drive under true synchronous mode. So, let us discuss about drive under self control mode. synchronous motor drive under self controlled mode. Now, we can take an example. This is a self controlled synchronous motor drive. Employing load commutated thyristor converter. Employing load commutated I will say thyristor converter, which is a CSI, So, let us see a self controlled synchronous motor drive employing load commutated thyristor converter, which is a current source inverter. So, we have two converters here. So, one is a source side converter. This is a source side converter using SCRs. And we have a DC link here. DC link has a large inductor to almost keep the current ripple free. Then we have a CSI, which is a thyristor converter, which has got 6 SCRs. So, this is a thyristor converter and this is feeding the stator of a synchronous motor. So, this is phase C, the phase B here, and we have the phase A. So, this is A, B and C. The field is separately excited. This of course has a field winding, the field is separately excited and this is fed from a DC supply. Now, the synchronous motor is connected to a position sensor. So, this is a position sensor, rotor position sensor, which will give us the position as well as the frequency of the rotor. Now, the input converter also has got SCRs. The input is supplied from the 3 phase AC. We can call this to be phase A prime, B prime, C prime. This is 3 phase AC supply. The inductor is in the DC link. So, the inductor is large enough to keep the DC link current almost ripple free. So, ID is almost constant and ripple free. Now, we have to trigger the source side converter. So, source side converter, this is the source side converter. This is triggered at an angle alpha s. So, the triggering angle of the source side converter is alpha s. This is the load side converter. Load side, the load is a synchronous motor, load side converter, and the triggering angle of the load side converter is alpha L. Now, how do we trigger the load side converter? The load side converter is triggered with the information from the rotor position sensor. because the rotor and the stator of a synchronous machine has to be perfectly synchronized. That is the principle of self controlled synchronous motor drive. So, in this case we get the information from the rotor position sensor. Here we have the triggering circuit, and the triggering circuit gets the information from the rotor position sensor. In fact, the information that we get is the rotor angle, phase angle. So, is the phase information, phase and frequency information, phase and frequency. So, the triggering circuit applies the triggering pulses to the load side converter at an appropriate angle, and the triggering angle is alpha L. Now, this load side converter can be named as T1, T2, T3, T4, T5 and T6. Similarly, the source side converter has got 6 SCR, can be named as T1 prime, T2 prime, T3 prime, T4 prime, T5 prime and T6 prime. Now, the nomenclature of these SCRs are such that this is the way they will be triggered: T1, T2, T3, T4, T5 and T6, and again after that, after T6 we again trigger T1. So, this is the nomenclature that we follow, and these are the currents which are flowing into the synchronous motor stator. This is IA, IB and IC, and the synchronous motor has got induced EMF or the back EMF, and this also has got inductances. So, each phase will have some inductance. So, we can show them as some inductance here, some inductance in phase B, some inductance in phase C. So, these inductances are called commutating inductance LC, LC and LC. Now, this load side converter which has got SCRs, which is also known as a CSI, current source inverter. Now, these have to be commutated by the back EMF of the synchronous machine, because these SCRs do not have any force commutation circuit. When they are triggered, they have to be turned off by the back EMF. So, this is called load commutated thyristor converter, because this thyristor converter is commutated by the load which is the back EMF of the synchronous machine. Now, let us try to understand how this is commutated. Now, the triggering pattern would be something like T1, T2, T3, T4, T5, T6, T1, T2. This is how it is triggered: T2, T3, T3, T4, T4, T5, T5, T6, T6, T1, and then it repeats T1, T2. So, at any given instant, 2 SCRs of the load side converter will be on, either T1, T2. This is the ideal case. This is the ideal case. Now, the load current ideally will have a quasi rectangular nature. Now, if we see the load current IA, the ideal current waveform will be that of a CSI, would be something of this sort. So, this is the load current has a amplitude here is ID. This amplitude also in the negative direction is also ID. So, this is against T or omega T. So, this is 180 degree pi and this is 2 pi, and the duration of this is 120 degree, and the the duration of the negative pulse is also 120 degree. So, this is a quasi square waveform. So, the nature of this waveform of the load current is a quasi square waveform, and this is the ideal waveform. Now, the phases has got inductance. When the phases has got inductance, the current change will not be so sharp. In fact, the practical current change will not be like this. So, if we see the practical change of the current, this will be different from what we just saw. So, this is the ideal nature that we saw, and the practical would be something different from that. This is omega t axis, the x axis. The practical waveform would be like this. It will be delayed. So, this is the waveform of I A that we are plotting, any phase current, and this delay is called the overlap. This delay is called the overlap angle, that is mu. Mu is called the overlap angle, and because of this delay we have the triggering or the conduction T1, T2, T3, T2, T3, T4, T3, T4, T5, T4, T5, T6, T5, T6, T1, T6, T1, T2, and then T1, T2, T3. So, the cycle repeats here. So, for a brief time when we trigger let us say T1, T2, T3, when we trigger T3, T1 does not turn off. So, it basically takes some time. So, this is the way it conducts. Now, let us try to understand the commutation process. So, let us draw the waveform, the circuit diagram first. So, we have the converter, the load side converter, which we can rewrite once again. And this the load is replaced by the back EMFs. So, what we can show here is the load, we have the inductances here, and we have the individual back EMFs of the various phases. So, these are the various phases we have. So, this is the back EMF, which is VAN, this is VBN, and this is VCN, and this is the neutral point N, and these are connected to the converter in the following fashion. So, these are the inductances of the machine. So, LC are the inductances of the machine. So, this is phase A current IA, this is phase B current, and this is phase C current IC, and this is the DC link that we have, and the DC link has got an inductance, and this current in the DC link is ID. So, the SCR is T1, T2, T3, T4, T5 and T6. So, let us now say that we analyze this commutation by drawing the voltage waveforms. The voltage waveforms which are in the line, this is phase A, this is phase B and this is phase C. The load is an active load. The load also has got back EMF. So, the load voltages are also sinusoidal. So, we can draw the various load line voltages for the synchronous machine. So, we can draw here VAB, VBC and VCA. So, if we draw the load voltages, they will appear like this. This is, let us say, one of the load voltages, that is VAB. Then we have the second load voltage, which is VBC, phase shifted from VAB by 120 degree. Then we have the third load voltage, which is VCA. This is VCA. So, and then we also have the inverse of that. So, this voltage is VAC, and then we have inverse of this voltage, that is VBA, and then we have inverse of this voltage, which is VCB. This is also VCB, and we can also draw in the negative side of these voltages. This also we can draw the negative side. So, these waveforms are all symmetrical. So, if we see in an oscilloscope, we will be able to see the various 3-phase voltage waveforms. Now, this is VCB as well. Okay. Now, what we are trying to do here, we are trying to analyze the commutation process. So, we start from this instant. We start from this instant. So, our voltage should have been VAB, but we delay it. So, we delay, we give a triggering angle. So, we apply a triggering angle which is alpha L. So, this angle is alpha L. So, this is our triggering angle alpha L. And then we try to switch to VAB, and in that process we have an commutation overlap like this. Similarly, at this instant we trigger the other SCR and we have a commutation overlap. Similarly, at this instant we apply the triggering pulse. So, we have a commutation overlap and the output looks like this. Similarly, here we have a commutation overlap and the output somehow looks like this. So, this is the nature of the output. Here again we have a commutation overlap. So, the output of the converter, the DC voltage looks like this. So, the DC voltage we are talking about is this DC voltage VD load side. So, this voltage is plus minus. So, this inverter or this converter is actually operating in the inverting mode. It means the energy is being supplied from the DC to the motor. So, this is the flow of the power, this is the flow of the power P. So, this converter is operating operating as an inverter. So, when it operating as an inverter, we have the triggering angle alpha L is greater than 90 degree. So, the analysis of this will show that there is a slow transition from one SCR to other SCR. We will be discussing the analysis of the commutation process in the next lecture.